These are the answers to the AP Chemistry Practice Midterm exam, starting with the multiple choice questions. Number 1. According to the information in the table above, a 1 gram sample of which of the following contains the greatest mass of oxygen? So the correct answer is the compound that has the greatest percentage of oxygen by mass. If we were to calculate the percentage of oxygen for the first choice, calcium oxide, it would be the mass of oxygen, so 16, divided by the total mass times 100. But since we cannot use a calculator to solve this question, we need to estimate the values to determine the correct answer. So we'll estimate that this ratio is 16 over 56 for right now. Since the second choice, sulfur dioxide, has 2 oxygens, it's going to be 32 divided by the total mass, which we'll say is 64. For our third choice, the vanadium oxide compound, there's 3 oxygens. That would be 48 divided by the total mass, which we'll estimate to be 150. And then finally, for the barium sulfate compound, 4 oxygens means 4 times 16, 64, divided by the total mass, 233. Now again, without a calculator, we can see that the choice B, the sulfur dioxide, that works out to be 50%. Any choice that is less than 50% can be eliminated. So choice A, 16 over 56 is definitely less than 50%, so we can eliminate choice A. 48 over 150 is also less than 50%, and 64 over 233 is less than 50%. So the compound that contains the greatest percentage of oxygen by mass would be B, sulfur dioxide. In number 2, we have a metal iodide compound with the formula Mi, and the charge on the metal is +1. It is dissolved in water and then reacted with excess silver nitrate, and it forms silver iodide as a precipitate. So the balanced equation for what's going on in this experiment is Mi plus AgNO3, and it produces AgI and MnO3. So the silver iodide is the precipitate. Since we don't know the identity of the mystery metal, we have to figure out how many moles of silver iodide were produced. Then we can figure out that must be the number of moles of Mi that reacted. So what mass of silver iodide was produced in this experiment? Based on the data, if we subtract 3.251, the mass of the filter paper plus the precipitate, minus the filter paper itself, we get 2.35 grams of silver iodide. Now that's convenient since the molar mass of silver iodide is 235. That means that 2.35 divided by 235 is exactly 0.01 moles of silver iodide produced. And based on the 1-to-1 mole ratio between the unknown metal iodide and silver iodide, there must have been 0.01 moles of metal iodide that reacted. So we know the mass of the metal iodide compound was 1.66 grams, and we know that that was equivalent to 0.01 moles. So the molar mass of this mystery compound is 1.66 divided by 0.01, and that works out to be 166 grams per mole. So now we have 4 choices: lithium iodide, sodium iodide, potassium iodide, and rubidium iodide. All we have to do is figure out from the periodic table which one of these compounds has a molar mass of 166 grams per mole. If we subtract 127 from 166, 127 is the mass of iodine. That means that the metal has a mass of 39. So the correct answer is potassium iodide, which has a molar mass of 166 grams per mole. In number 3, it says complete combustion of a sample of a hydrocarbon in excess oxygen produces equimolar quantities of carbon dioxide and water. And we're trying to figure out the molecular formula of this compound. So the balanced equation we can't really do since we don't know the formula of the hydrocarbon. So what does equimolar quantities mean? That just means we have the same number of moles of carbon dioxide as we have water. So let's assume that 1 mole of carbon dioxide was produced and 1 mole of water was produced in this reaction. Now, how can we determine the empirical formula of the hydrocarbon from this information? Well, to figure out how much carbon was present, if 1 mole of carbon dioxide was produced, that means there must have been 1 mole of carbon in the original compound. And if 1 mole of water was produced, that would have been 2 moles of hydrogen atoms in the original hydrocarbon. So therefore, we can figure out the empirical formula of the hydrocarbon. And since the empirical formula must be CH2, then the correct answer is choice C. C4H8 has an empirical formula of CH2. And if you go ahead and balance the combustion equation for C4H8, the final coefficients would include 4 moles of carbon dioxide and 4 moles of water. So it is indeed equimolar quantities of those chemicals. In number 4, we are presented with successive ionization energy values, so first, second, third, fourth, and fifth, for an element in the second period. So we know the answer is either boron or nitrogen. Boron has 3 valence electrons, and nitrogen has 5 valence electrons. Since we can see a rather large increase in the energy between the third and the fourth ionization energy, that means that this particular element has 3 valence electrons, so the correct answer is A. In number 5, we are given a photoelectron spectra. We're just focusing on the 1s electrons, but there are 2 different species, calcium 2+ and argon. And again, the word isoelectronic means same number of electrons, so both of these species have 18 electrons. Now calcium, of course, has 20 protons, whereas argon has only 18 protons. That difference in protons is very important. Peak X has a higher binding energy, which means that the electrons are more difficult to remove from the atom. So the electrons must be more attracted to the nucleus. And therefore, since calcium has more protons than argon, the correct answer is that peak X corresponds to the calcium ion because its nucleus contains 2 more protons than that of argon. Number 6, we are given the information for calcium about atomic radius and the first ionization energy, and we have to predict the values for potassium. So we should know the following periodic trend for atomic radius. That atomic radius will decrease in general from left to right across a period. That means that the atomic radius of potassium is larger than that of calcium. So we're looking for a number that is greater than 174 for the atomic radius. So the correct answer is either C or D. Now in terms of the trend for the first ionization energy, those values tend to increase from left to right across a period, and since potassium is further to the left in the same period, potassium should have a lower first ionization energy than that of calcium, looking for a number that is less than 590, so the correct answer for number 6 is C. In number 7, we are given a mass spectrum for an unknown element, and we can tell that the average atomic mass of this element must fall somewhere between 63 and 65. If we look on the periodic table, the only element that has an average atomic mass between 63 and 65 is copper. So we can eliminate choice D, which says the average mass is going to fall between 64 and 65. We know this is copper. We know the correct answer is A, since copper contains 29 protons. In number 8, it involves an acid-base titration, and we can tell that benzoic acid is a monoprotic acid, so it has only 1 proton or 1 H+ ion that it's going to use in this reaction. The overall balanced chemical equation for a monoprotic acid would be a 1-to-1 ratio between the acid and, in this case, the strong base, sodium hydroxide. It produces water and then sodium benzoate. Now, as far as figuring out moles, we don't know the molarity of the sodium hydroxide solution, but we do know a way of figuring out how many moles of benzoic acid were used. Since 1.22 grams of benzoic acid were used, again, there's a 1-to-1 mole ratio between the acid and the base. We take that 1.22 grams, divide by the molar mass of benzoic acid, 122, 0.01 moles of acid was used, so therefore 0.01 moles of base, sodium hydroxide, was used. Now that we know 0.01 moles of sodium hydroxide, we divide moles by liters to get molarity. The volume of sodium hydroxide is 50 milliliters, or 0.05 liters. So 0.01 divided by 0.05, that's fairly easy mental math. That's going to be 1/5, or 0.2. So the correct answer is C, 0.2 moles per liter. Number 9 involves an experiment in which we have solutions of copper sulfate with different concentrations, and the absorbance is measured using what's called a spectrophotometer. So what exactly is a spectrophotometer? In this experiment, they're going to put these solutions into a little cuvette, which is a square holder that's going to hold the solution. Light is traveling through the solution, and then it's going to reach a detector. And the darker the solution is, the greater the absorbance value will be. So you can use spectrophotometry to calculate the concentration of solutions that absorb visible light. So this copper sulfate is a blue solution. When a sample of copper sulfate is placed in a cuvette, the absorbance can be measured with a spectrophotometer. And the more concentrated the solution is, the greater the absorbance value will be. So why is the absorbance value for the 0.4 molar copper sulfate solution too low? Well, considering choices A and B talk about either the cuvette had scratches on it or the cuvette had fingerprints on it, both of these would actually prevent some of the light from reaching the detector. If those errors occurred, then the absorbance value will be higher than it should be, because again, it's blocking the light from reaching the detector. So the solution would seem darker than it really is. But the absorbance value is too low. So looking at choice C, all we're saying in choice C is that the cuvette was filled slightly more than the other cuvettes. But as long as light travels through the solution, the fill level is not going to make a difference. As long as there's enough solution to cover the path of light, that's fine. Take a look at choice D. The absorbance is too low because it looks like the concentration of the solution is too low. So the lower the concentration of the solution is, the smaller the absorbance will be. And if there had been some water droplets inside the cuvette before the solution was added, the concentration of that solution would be diluted to a lower value. Correct answer is D. Number 10, we have an experiment in which hydrogen reacts with oxygen. So let's write a balanced chemical equation for this. We have 24 grams of hydrogen. That would equal 12 moles of hydrogen gas. We have 48 grams of oxygen, and that would equal 1.5 moles of oxygen gas. Again, this is fairly simple mental math without a calculator. Now to convert into product, which is water, 12 moles of hydrogen gas would produce 12 moles of water. But 1.5 moles of oxygen gas could only produce 3 moles of water. That makes oxygen the limiting reactant, and the theoretical yield of water is 3 moles. So how many grams is 3 moles of water? Well, since 1 mole of water weighs 18 grams, 3 times 18 is 54. So the correct answer for number 10 is C. Number 11. we have three different containers that hold a different sample of gas. We have hydrogen, we have CH4, which is methane, and we have sulfur dioxide. Now the pressure in the sulfur dioxide container is slightly less than in the hydrogen and the methane. Each of these samples contains 1 mole of gas. So 2 grams of hydrogen, 16 grams of methane, and 64 grams of sulfur dioxide. So we're trying to figure out why the pressure in the sulfur dioxide container is slightly less than the other two. According to the kinetic molecular theory, the pressure, which is caused by the collisions of the gas molecules with the container walls, it's going to be exerted by molecules colliding, and we assume that these particles do not experience any attractive or repulsive forces. But if the gas particles experience any intermolecular attractive forces, then the pressure would be slightly less than the value predicted by the ideal gas law. So does sulfur dioxide experience attractive forces more than, let's say, hydrogen or methane? And the answer is yes, because sulfur dioxide is a polar molecule, and it would experience dipole-dipole forces. Hydrogen and methane are nonpolar, and they would experience only weak London dispersion forces. So again, it's the strength of the intermolecular attractive forces that causes a slight decrease in pressure for the sulfur dioxide. In number 12, we have a particle diagram to go with this question. The reaction is between nitrogen monoxide, NO, and oxygen gas, O2. The product is nitrogen dioxide, NO2. Now, it turns out that the pressure is going to be monitored before the reaction and after the reaction. Our balanced chemical equation between NO and O2 looks like this. So 2 molecules of NO react with 1 molecule of oxygen to produce 2 molecules of nitrogen dioxide. So if you count the particles, before the reaction we have a total of 12 molecules of gas. After the reaction, we have a total of 8 molecules of gas. And we're monitoring the pressure. What's not changing in this experiment would be the volume, because it's a rigid container, and the temperature is constant. So pressure is proportional to the moles of gas. Since there is an overall decrease in the number of molecules of gas in the container, then the pressure should decrease. The correct answer is B. Number 13, we have a chemical reaction. We are given a delta H value of positive 91 kilojoules per mole, and the reaction takes place in a rigid insulated container that is initially at 600 Kelvin. Which of the following describes what happens to the temperature of the contents of the vessel as the reaction occurs and provides the correct justification? Let's talk about endothermic versus exothermic. So an endothermic reaction, heat flows from the surroundings to the system, whereas in an exothermic reaction, heat flows from the system to the surroundings. So we're monitoring the temperature. Typically that thermometer is part of the surroundings. So with an endothermic reaction, the temperature of the surroundings decreases. With an exothermic reaction, the temperature of the surroundings increases. We, in this particular reaction, know that the delta H is positive, so it's endothermic. Therefore, our thermometer, which is part of the surroundings, would measure a decrease in temperature because the reaction is endothermic. In number 14, the question asks, what is the final pressure in the vessel after the reaction is complete? So we started with a pressure of 3 atmospheres. And based on the balanced chemical equation, we're going to look at moles here. Since the volume is not changing, the rigid reaction container, that volume is constant, and temperature is not changing, the pressure would change based on changes to the number of moles of gas. So we started with a pressure of 3 atmospheres, and we have 1 mole of reactants. We have a total of 3 moles of products. Since we're going from 1 mole to 3 moles, that means that the pressure should increase by a factor of 3. And since the initial pressure was 3 atmospheres, the final pressure should be 9 atmospheres. Correct answer is D. In number 15, we have a paper chromatography experiment, and this is about polarity. So the correct answer is either C or D. We're comparing the polarity of component X and component Y. Now the solvent that's traveling up the paper is hexane, which is non-polar. Since component X is able to travel up the paper faster than component Y, then X is able to interact more easily with a non-polar solvent. So X is more of a non-polar substance than Y is. You could also say that since Y is more attracted to the polar paper itself, then Y is more polar than X, which is why it moves more slowly up the paper. So Y is more polar than X. The correct answer is D. Number 16 shows us net ionic equations for a reaction between an acid and a base. The base happens to be a strong base, sodium hydroxide. So for the net ionic equation, all we have to write is the hydroxide ion, OH-. But if the acid is weak, we leave that acid written together as one formula. If the acid is strong, then we only write H+, because the acid would be split up and we'd cross off the spectator ions. So the determination of whether the acid is strong or weak comes from the particle diagram. On the left, the majority of HX molecules are not ionized. So HX is a weak acid. But on the right, the majority, I guess 100% in this case, of the HY molecules are fully ionized. So HY is a strong acid. For a weak acid, we should leave that formula written together. So HX, the correct answer is either A or B. And then for the strong acid, we should split it up completely and just write H+, and OH- makes water. So the correct answer is choice B, which shows a weak acid in column 1 and a strong acid in column 2. In number 17, we are given 2 hydrocarbons, pentane and octane, and we're trying to figure out the substance that would be present in the higher concentration in the distillate. So for distillation, that has to do with a separation based on boiling point. So which of these compounds has a lower boiling point? Well, since both pentane and octane are hydrocarbons, they are nonpolar, they experience weak London dispersion forces. How do we compare the strength of the London dispersion forces? Well, it's based on the size of the molecule or the size of the electron cloud. Larger molecules are more polarizable and have stronger London dispersion forces. So in this case, octane is the larger molecule and has a higher boiling point than pentane. When this mixture is distilled, pentane will be the first chemical to appear in the first few drops of condensed liquid. So here is a setup of a distillation apparatus. And again, the first chemical to appear in the distillate is the one with the lower boiling point. So the correct answer is B, pentane, because it has a shorter carbon chain and weaker London dispersion forces. In number 18, we have a particle diagram. We're starting with a solution of lead nitrate. And if we count the lead cations in that diagram, there are 5 lead ions. Then we have sodium iodide, and if we count those cations, we actually have 10 sodium ions. So what does the particle diagram tell us about the relative concentrations for these two solutions? Well, it tells us, since these two solutions have the same volume, that the concentration of sodium iodide is twice as much as the concentration of lead nitrate. So the correct answer is either C or D. Now we take those 10 sodium ions, which are currently in 1 liter. Those 10 sodium ions will now be in a total volume of 2 liters. So the concentration of sodium is cut in half at the end of the equation. So the correct answer is D, which shows that the final concentration of sodium ions is actually half as much as the concentration of sodium ions before the reaction begins. Number 19 has the same concept that we saw in number 17. We have two hydrocarbons, and we're going to compare the strength of the attractive forces. Again, these are both nonpolar hydrocarbons that experience weak London dispersion forces. Because butane is a larger molecule, has a larger electron cloud than ethane, we would expect butane to experience stronger London dispersion forces and have a higher boiling point. So the correct answer is B. Butane has greater polarizability and stronger dispersion forces. In number 20, under what conditions will a gas behave most like an ideal gas? You want to minimize the attractive forces between the molecules, so you want the molecules moving very fast and very far apart. So the best conditions for ideal gas behavior are low pressures and high temperatures. So correct answer would be C, which has a low pressure and a high temperature. Number 21. We have 4 particle diagrams. Which of the following best illustrates the hydrogen bonding interaction between two molecules of methanol, CH3OH? So remember that hydrogen bonding is an intermolecular attraction between two molecules, and in order for a molecule to have hydrogen bonding, there must be a hydrogen atom directly attached to either a fluorine, oxygen, or nitrogen. So we definitely have a hydrogen directly attached to an oxygen on the molecule methanol. The problem with choice B and the problem with choice D is that we don't have opposite atoms. We have either 2 hydrogens or 2 oxygens. So now we've narrowed down the choices to either A or C. Now the problem with choice C is that the hydrogen atom that is participating in the hydrogen bond is directly attached to carbon, and that is not the most polar bond in that molecule. So for this hydrogen bonding interaction, the hydrogen that is doing the reaching out and attracted to the other molecule, that hydrogen needs to be directly attached to either oxygen, fluorine, or nitrogen. So correct answer for number 21 is A. Number 22 talks about lattice energy. Let's remember Coulomb's law. In Coulomb's law, the lattice energy increases as the charges on the ions increase, which means that a +2 -2 attraction would have a greater lattice energy. So the correct answer is either C or D because of the magnitude of the charges. It also says lattice energy increases as their radii decrease. So which of these pairs of ions have a smaller ionic radii? That would be the best choice. Now barium and sulfide are larger in size than magnesium and oxide. So correct answer, higher magnitude of charge, smaller ionic radii is A. In number 23, which of the following best helps explain why the value of delta H for the dissolving of calcium fluoride in water is positive? Now when an ionic solid dissolves in water, there are 3 processes. One of these processes is breaking the attractive forces between the ions. Okay, that's going to be endothermic. The other would be breaking the attractive forces in the solvent, in this case the water, that's also endothermic. And then forming the ion dipole forces, the attractive forces between the solute and the solvent, well, that's going to be exothermic. And since the delta H for the dissolving of calcium fluoride in water is positive, we are looking for an endothermic process. So choice A talks about the temperature of the solution increasing. If that's the case, that would mean releasing heat to the surroundings. That's exothermic, so the correct answer is not A. B talks about conducting electricity and does not talk about heat, so it's not B. And then choice D talks about forming these ion dipole forces, again, that would be an exothermic process. So we've narrowed down all the choices to the correct answer. The reason why the correct answer is C is because if you're breaking strong ion-ion interactions between calcium ions and fluoride ions, that would be an endothermic process. Number 24 is talking about properties of liquids. We're given the molar mass and the boiling point for two liquids, and we have to determine which one of them has the higher equilibrium vapor pressure and explain why. And we know it has to do with the strength of the London dispersion forces because these two compounds are both nonpolar. Let's compare two liquids in general. The liquid on the left is shown to have a lower vapor pressure, and the liquid on the right has a higher vapor pressure. So what could we say about boiling point and the strength of the intermolecular forces? Well, the liquid on the left, because it has a lower vapor pressure, that means it's going to have a higher boiling point and stronger intermolecular forces, whereas the other liquid on the right would have to have a lower boiling point and weaker intermolecular forces. Now let's compare these two diagrams with the data in the table. CS2, carbon disulfide, has a lower boiling point and therefore should have a higher vapor pressure, whereas carbon tetrachloride, CCl4, has a higher boiling point and therefore should have a lower vapor pressure. So the correct answer is carbon disulfide, CS2. Why would it have a higher vapor pressure? Because it has weaker London dispersion forces. In number 25, we have a reaction between sodium chloride, NaCl, and silver nitrate, AgNO3. The products are silver chloride, AgCl, and sodium nitrate. Now look closely at the quantities of reactants. We can see from the balanced equation that there is a 1-to-1 mole ratio between sodium chloride and silver nitrate. But notice that they used 50 milliliters of 0.1 molar sodium chloride and 50 milliliters of 0.2 molar silver nitrate. That means there's an excess amount of silver nitrate. In terms of the particle diagram, if there's an excess amount of silver nitrate, at the end of the reaction there should still be silver ions and nitrate ions present in the solution. We can eliminate choices A and B because there are not both silver and nitrate ions present in the solution at the end. Now, since the excess reagent is silver nitrate, that means that the limiting reactant is the sodium chloride. All of the chloride ions should have reacted completely. There should be no chloride ions still present in the solution at the end. So we can eliminate choice C because there should not be any chloride ions present in the solution. All of it reacted to produce the precipitate. Correct answer is D. Number 26. We are comparing carbon dioxide, CO2, with sulfur dioxide, SO2. Now the molecular geometry, it looks like these molecules are drawn as linear. However, the carbon dioxide is linear and the sulfur dioxide is actually bent. Just because a Lewis structure looks like a straight line doesn't necessarily tell you what the actual shape of the molecule will be. So these two molecules have different molecular geometry, so the correct answer is either C or D, and it's because of that lone pair on the sulfur atom that creates the bent shape. So it's 2 electron domains versus 3 electron domains on the central atom. Correct answer is D. Number 27. On the basis of the information in the table above, which of the following has arranged these 3 bonds in order of increasing bond polarity? So electronegativity and bond polarity is such that when we compare the electronegativity values, the greater the difference in electronegativity between 2 atoms, the more polar that bond will be. Let's start with carbon and hydrogen. The difference is 0.4. Then let's take a look at silicon and chlorine. The difference is 1.2. And now let's take a look at the difference between sulfur and fluorine, and that difference is 1.5. So in order of lowest to highest, increasing bond polarity, the correct answer for number 27 is A. In number 28, we have a reaction between hydrochloric acid, HCl, and sodium carbonate, Na2CO3. Before we take a look at the products of the reaction, let's consider what's happening right now. We have HCl, that's H plus and Cl minus, and then we have Na2CO3, that's sodium plus, and carbonate CO3 2 minus. Let's imagine that it's a double replacement reaction. So sodium would bond with chloride to give sodium chloride, and the H plus would bond with the CO3 to give H2CO3. Now, are these in fact the products of the reaction? Well, it said that bubbles of CO2 are produced. So what happens is the H2CO3 rapidly falls apart to give water and CO2. Here we have our unbalanced equation. Let's balance the equation by putting a 2 in front of the HCl and a 2 in front of the sodium chloride. And notice that there is a 2-to-1 mole ratio between HCl and Na2CO3. Now let's analyze how many moles of HCl we have. So volume times molarity equals moles. 0.1 liters times 6 moles per liter, that gives us 0.6 moles of HCl. Now with the Na2CO3, they've given us 10.6 grams, and since the molar mass is 106, 10.6 divided by 106 is exactly 0.1. So we have clearly a large excess of HCl. We have way more than the 2-to-1 mole ratio that we need. Since HCl is an excess, that means that the sodium carbonate is the limiting reactant. The limiting reactant will determine how much product we can make. What is the theoretical yield of sodium chloride? Well, it starts with 0.1 moles of sodium carbonate. That would produce 0.2 moles of sodium chloride. Since they want the answer in grams, we're going to take 0.2 moles of sodium chloride and multiply by 58.5. That's fairly easy mental math. 58.5 times 2 is 117. So 58.5 times 0.2 is 11.7. Correct answer is C. Number 29. We have a balanced equation between iron and hydrochloric acid. The student adds 30 milliliters of 1 molar hydrochloric acid to 0.56 grams of iron. Let's start with the 30 milliliters. That would be 0.03 liters. So we have 0.03 moles of hydrochloric acid. And since on the periodic table we can estimate that the molar mass of iron is about 56 grams, 0.56 grams of iron is 0.01 moles of iron. Now considering that the mole ratio between iron and HCl is 1-to-2 in the balanced equation, we actually have a 1-to-3 ratio between iron and hydrochloric acid. That gives us an excess amount of hydrochloric acid, and the iron is the limiting reactant. Since the iron is the limiting reactant, then all of the iron is consumed, so the correct answer cannot be A. There will be no iron left over at the end. With respect to the hydrochloric acid that does react, 0.01 moles of iron reacts with 0.02 moles of HCl. That leaves 0.01 moles of HCl left over at the end, so the correct answer could not be B. As far as the iron chloride, there is a 1-to-1 ratio between iron and iron chloride. So we're going to produce 0.01 moles of iron chloride. So the correct answer could not be C. Now, as far as why the correct answer is D, we are under STP conditions, 273 Kelvin and 1 atmosphere. That means that 1 mole of gas occupies a volume of 22.4 liters. And if we're going to produce 0.01 moles of hydrogen times 22.4 liters per mole, we're going to produce 0.22 liters of hydrogen. So the correct answer is, in fact, D. In number 30, the question says, which element is being reduced and what is the element's change in oxidation number? Well, iron is changing from 0 to +2, but that's an example of oxidation. Chlorine is -1 on both sides of the equation, so it's not changing at all. And the hydrogen is changing from +1 to 0, which is an example of reduction. So the correct answer for number 30 is B. In number 31, we're talking about the combustion of methane. So CH4 reacts with oxygen to produce carbon dioxide and water. A combustion reaction is exothermic. The sign of delta H is negative, so the correct answer is either A or C. And the reactants should have a higher enthalpy than the products, so we're essentially going downhill, energetically speaking. So correct answer for number 31 is C. In number 32, we're talking about bond length and bond energy, or enthalpy. We have two molecules, C2H2, which has the following Lewis structure, and C2H6, which has a different Lewis structure. So we have a triple bond versus a single bond. Now, in terms of bond enthalpy and bond length, a single bond is going to be longer and have a lower bond enthalpy. A double bond would be shorter and have a higher energy, and a triple bond is even shorter and even higher. So the C2H2 has a shorter bond length and a higher bond enthalpy, so it's harder to break. Where would that be a good choice? Choice B shows that C2H2 has a shorter bond length and a higher bond enthalpy. Number 33 is talking about the relationship between hydrogen and helium. Now, they have different masses. So what is the relationship between the molar mass of a compound and its average speed? Well, the effect of molar mass on molecular speed is that heavier particles tend to have a smaller speed, so they're slower. Lighter particles have a higher speed, they're faster. Since helium is heavier than hydrogen, the average speed of helium should be less than that of hydrogen. So the correct answer that shows this is choice A. Number 34 is about calorimetry and calculations that, again, we can do without a calculator. We know that 8.4 kilojoules of heat was transferred from a hot iron ball to a sample of water. 8.4 kilojoules is 8,400 joules. We're going to use Q equals mc delta T. 8,400 joules of heat transferred to 200 grams of water, and the specific heat capacity of water is 4.2 joules per gram degree Celsius. So what we don't know is the delta T, the change in temperature of the water. Now, since 200 times 4.2 would be 840, 8,400 divided by 840 is equal to 10. So our delta T is 10. The water was initially at 25 degrees, so the final temperature of the water is 35 degrees. Number 35 involves a reaction between magnesium oxide, MgO, and hydrochloric acid. This is a limiting reactant problem. We begin with 4 grams of MgO, which has a molar mass of approximately 40, so we have 1/10 of a mole of magnesium oxide. We have volume times molarity to get moles of HCl, so 0.1 liters times 4 moles per liter, that's 0.4 moles of HCl. The ratio between magnesium oxide and HCl should be 1 to 2 in the balanced chemical equation. But we actually have 4 times as much HCl compared to MgO. So the HCl is in excess, and the magnesium oxide is the limiting reactant. Since the magnesium oxide is the limiting reactant, the answer is either A or B. And if 150 kilojoules of heat is produced for every 1 mole of MgO that reacts, that means that 15 kilojoules of heat is released when 0.1 moles of MgO reacts. The correct answer for 35 is A. Number 36 is about bonds broken and bonds formed. So in this reaction, we are breaking an HH bond, that's 430 kilojoules. We're also breaking a chlorine-chlorine bond, that's 240 kilojoules. And we are forming, in this reaction, two HCl bonds, so 2 times 430 kilojoules. Total energy absorbed when the bonds are broken is 430 plus 240, that's 670 kilojoules, that's positive. Total energy released would be negative 860, that's the change. So we're going to do bonds broken minus bonds formed. 670 minus 860, that is negative 190, and the correct answer is C. Number 37, there's a lot of data to process. Let's go ahead and take a look at each of the combustion data separately. So we have the cashew that was burned, and we have the marshmallow that was burned. The data for the cashew is that 1,000 grams of water, so MC delta T, times 4.2 joules per gram degree Celsius, and a delta T of 5 degrees. So the math there would be 5,000 times 4.2, that would give us the total number of joules of heat released when the 1 gram of cashew was burned. For the marshmallow, we have 2,000 grams of water. Again, the specific heat capacity of water is the same, and our delta T is also 5 degrees Celsius. That would be the math, 10,000 times 4.2. So in terms of the heat released for the marshmallow, that would be 42,000, and the heat released for the cashew, that's actually half as much, would be 21,000. So here's what we know so far. When the cashew is burned, it's 21,000 joules of heat per gram, and when the marshmallow is burned, it's 42,000 joules, but that's for 3 grams. Now if we divide 42 by 3, we get that's around 14,000 joules per gram. So now with this data in front of us, we can definitely pick the correct answer, which is C. The combustion of 1 gram of cashew would release more energy than the combustion of 1 gram of marshmallow. Number 38 is about formal charge. Let's go ahead and assign formal charges to each atom in each choice. Starting with choice A, 4 would be the valence electrons for carbon. That's going to be 4 minus 7, so negative 3. For nitrogen, it's going to be 5 valence electrons, so 5 minus 4 is positive 1. And for oxygen, 6 valence electrons is going to be 6 minus 5, that's positive 1. If we do the same thing for the other choices, we have for nitrogen, 5 minus 7 is negative 2. Carbon, 4 minus 4, 0. And oxygen, 6 minus 5, positive 1. For choice C, carbon, 4 minus 5, negative 1. Nitrogen, 5 minus 4, positive 1. And oxygen, 6 minus 7, negative 1. And then finally, choice D, nitrogen, 5 minus 5, so 0. Carbon, 4 minus 4, 0. Oxygen, 6 minus 7, negative 1. The dominant Lewis structure is generally the one in which the atoms bear formal charges closest to 0. That makes D the best choice, and it puts a negative charge on the atom that has the highest electronegativity, which in this case is oxygen. So correct answer is D. Number 39 is about hybridization of the nitrogen atom in the NH3 molecule, and it's also about the bond angle in that molecule. So starting off with hybridization, after we draw the Lewis structure, we can count the number of electron domains off the central atom. In this case, we have 3 bonding domains and 1 non-bonding domain. That's a total of 4 electron domains, sp3 hybridization for the NH3 molecule. Now, as far as the bond angle, it is slightly less than the predicted 109.5 because the lone pair tends to repel and exert greater repulsive forces than a bonding pair. So less than 109.5 puts it about 107. So the correct answer for this question is C, sp3 hybridization and a bond angle of 107. Number 40, last multiple choice question. A sample of pure carbon dioxide in a rigid container has a pressure of 2 atmospheres at a temperature of 0 degrees Celsius. What is the density of this gas sample? Now remember, this is without a calculator. Let's take a look at the mental math we can do to get the answer to this question. What do we know about CO2? Well, we know that 1 mole of CO2 has a mass of 44 grams, and we know that if we were at STP, which is 1 atmosphere and 0 degrees Celsius, the volume would be 22.4 liters. Now we're not at STP. We have a temperature of 0 degrees Celsius, but we have a pressure of 2 atmospheres. So according to Boyle's law, if you double the pressure, then the volume decreases by half. So instead of 22.4, we would have a volume of 11.2 liters because we have 2 atmospheres and 0 degrees Celsius. All right, 44 grams, that's the mass of 1 mole. 11.2, that's the volume of 1 mole. The density under these conditions would be 44 divided by 11, which is 4 grams per liter. Correct answer is D.
And now on to the free response questions. Number 1, a student is given a sample of a pure anhydrous salt, which could be either lithium carbonate, sodium carbonate, or potassium carbonate. Part A, the student measures out 1 gram of the unknown salt and dissolves it into water. In the box below, complete a particle diagram that includes 4 water molecules with the proper orientation about the carbonate ion. Now, in terms of the direction, the positive end of the water molecule, which is the hydrogens, should be pointing toward the negative carbonate ion. So the 4 water molecules should be arranged with the hydrogen end pointing toward the carbonate ion, like that. In part B, calculate the number of moles of calcium chloride added to the solution. So we have 25 milliliters of a 1.6 molar calcium chloride solution. We're just going to do volume in liters, so 0.025 liters, times the molarity, and we get 0.040 moles of calcium chloride. Then it says write the balanced net ionic equation for the formation of the solid precipitate. A solid precipitate is formed which contains carbonate ions. So remember, we have the unknown metal carbonate, so M2CO3, where M is either lithium, sodium, or potassium, reacting with calcium chloride to produce 2 products, the soluble metal chloride and calcium carbonate. So the precipitate is the calcium carbonate. The ions on the left side of the equation are the calcium ion and the carbonate ion. There is your net ionic equation for the formation of the solid precipitate. In part C, we have some data about the precipitate. The precipitate is filtered, dried, and weighed. The mass of the precipitate would be 2.02 grams minus 0.65 grams. So we have 1.37 grams of calcium carbonate, the precipitate. Let's convert that into moles. We'll just take the 1.37 grams, divide by the molar mass of calcium carbonate, which is 100.09, and we get 0.01368. Let's round off to the proper number of significant figures. In this case, that would be 3 sig figs. So 0.0137 moles of calcium carbonate. Now, the next part says, the formula that is most likely to represent the unknown salt in this experiment is. Before we make this choice, let's go ahead and talk about the reaction. We have a 1 1 mole ratio between the unknown metal carbonate and calcium carbonate. We just learned that the moles of calcium carbonate is 0.0137. That means there is also 0.0137 moles of the unknown carbonate. And they gave us, in this particular problem, 1 gram of this unknown metal carbonate. Let's divide grams over moles. So the molar mass is 73. Looking at the molar masses of lithium, sodium, and potassium carbonate, the correct answer would be lithium carbonate. The molar mass is 73, which is closest to the molar mass of lithium carbonate. In part D, we are looking at a net ionic equation for the reaction between the metal carbonate and hydrochloric acid. We saw a reaction like this in the multiple choice section. Let's write the equation before we focus on the net ionic version. We take our metal carbonate, react it with HCl, and we're going to produce a metal chloride plus not carbonic acid, but rather water and CO2. We'll balance the equation by putting a 2 in front of the HCl and a 2 in front of the metal chloride. And in terms of solubility, the metal carbonate is an alkali metal carbonate, which is soluble in water. So that gets split up into its ions. Hydrochloric acid is a strong acid. That also gets split up into its ions. The metal chloride is soluble. That gets split up into its ions. Then we have water and CO2. Let's cross off the spectator ions on both sides of the equation. And we're left with the net ionic equation. So the carbonate ion plus H plus produce water and CO2. There is your net ionic equation. In number 2, we're given the structural formula of benzoic acid, and we are asked in part A to identify the hybridization of the carbon atom indicated by the arrow. Well, that particular carbon has 3 electron domains around it, so therefore it's going to be sp2 hybridization. In part B, we're looking at the intermolecular forces for these compounds, benzoic acid and acetophenone. The benzoic acid molecule is polar, so it's going to have London dispersion forces, and it should have dipole-dipole forces. Let's see if it has hydrogen bonding. Is there a hydrogen directly attached to an oxygen? Yes. So it's going to have London dispersion forces and hydrogen bonding. Now the acetophenone is also a polar molecule, but there is no hydrogen bonding. So London dispersion forces and dipole-dipole forces. Since hydrogen bonding is stronger than dipole-dipole forces, that means that benzoic acid should have stronger intermolecular forces and a higher boiling point. Acetophenone has weaker intermolecular forces and a lower boiling point. So the boiling point of acetophenone should be less than the boiling point of benzoic acid. And again, it's because hydrogen bonding is stronger than dipole-dipole forces, so therefore the intermolecular forces in benzoic acid are stronger than those in acetophenone. Benzoic acid has a higher boiling point than acetophenone. In part C, it's talking about a combustion equation. Let's go ahead and balance that equation. We have 7 carbons on the left, so we'll put a 7 in front of the CO2. We have 6 hydrogens on the left, so we'll put a 3 in front of the H2O. Now we have a total of 17 oxygen atoms on the right. And since there are 2 oxygen atoms in benzoic acid, that means we need 15 oxygen atoms to come from the oxygen, O2. So we'll balance the equation by putting a 7.5 in front of the O2. This equation is now balanced. Let's go ahead and double all these coefficients. Final coefficients 2, 15, 14, and 6. Now, they say that 1 gram of benzoic acid, when burned, produces 26.4 kilojoules of heat. Therefore, if we convert this from kilojoules per gram into kilojoules per mole of benzoic acid, we're going to take 26.4 kilojoules divided by 1 gram, and then multiply by the molar mass of benzoic acid. We get 3,224 kilojoules per mole. But since the balanced equation features 2 moles of benzoic acid, instead of 3,224, it's going to be 6,448. Don't forget, it's exothermic, so the delta H is negative 6,448 kilojoules per mole of reaction. All right, this next part, it says that 2.25 grams of benzoic acid was burned. How much heat was released? I'm going to show you 2 ways to calculate this equation. We could go back to the original statement about there's 26.4 kilojoules for every 1 gram of benzoic acid. We'll just multiply by 2.25 and we get 59.4 kilojoules of heat released. Another way to solve this question and get the same answer is we could use 2.25 grams of benzoic acid. We could first convert to moles, and then we could use the answer from the last problem where 6,448 kilojoules of heat is released for every 2 moles of benzoic acid burned. Either way, we get 59.4 kilojoules of heat released. Now, what can we do with this heat? We can see how much water is going to be affected by that. So this water is now being heated by the 59.4 kilojoules, or 59,400 joules. So 500 grams of water, again, Q equals mc delta T. We have our specific heat capacity of water, and we don't know the delta T. So we'll go ahead and solve for delta T, and we get 28.4 degrees Celsius. The final temperature would be 25 plus 28.4. The final temperature of the water, after it absorbs the 59.4 kilojoules of heat, is 53.4 degrees Celsius. Number 3. We're going to fill in the Lewis electron dot diagrams for each molecule. So for the carbon monoxide molecule, it looks like this. A total of 10 electrons with a triple bond. For the chlorine diatomic molecule, it's going to be a total of 14 electrons. And it's a single bond, looks like this. And then the last molecule, it's going to be a single bond for the carbon-chlorine connections, and a double bond between the carbon and the oxygen. A total of 24 electrons in that structure. Now, on to part B. Although the atoms in the Lewis diagram for the CO molecule obey the octet rule, the formal charge on each atom is not 0. So for the carbon, it's going to be 4 minus 5. That's negative 1 on the carbon. And for the oxygen, it's going to be 6 minus 5. That's positive 1. And in part C, the molecular geometry of the COCl2 molecule is going to be with 3 electron domains, trigonal planar. This molecule is not symmetrical, so it is polar. We have 3 sigma bonds, and we have 1 pi bond. In part D, we're going to do bonds broken minus bonds formed to figure out the delta H for this reaction. So what bonds are we breaking? Well, we're breaking the carbon-oxygen triple bond and the chlorine single bond. As far as the bonds we're forming, it's going to be a carbon-oxygen double bond and 2 carbon-chlorine single bonds. So total amount of energy absorbed, 1,314 kilojoules. Energy released in forming the bonds, 1,455. Therefore, the delta H for this reaction would be negative 141 kilojoules. The next part asks us to indicate whether the average kinetic energy of the carbon monoxide molecules is less than, equal to, or greater than the average kinetic energy of the chlorine molecules. Well, these two containers are at the same temperature, therefore the average kinetic energy of each gas is the same. So they are equal because they are at the same temperature. Now what about the average speed? Well, it's a different story here because now we are looking at the molar mass of each gas and they are different. So because the average speed of the CO molecules is based on mass, it's going to be greater than the average speed of the chlorine molecules. The molar mass of carbon monoxide is 28, whereas the molar mass of chlorine is 71, so lighter particles travel faster on average than heavier particles. In the next part, calculate the mass of carbon monoxide gas in the flask on the left. This will be an ideal gas law equation. We're solved for moles. So if PV equals nRT, that means that N equals PV over RT. The pressure is 2 atmospheres. The volume is 1 liter. We have the gas constant 0.08206, and 25 degrees Celsius becomes 298 Kelvin. This gives us approximately 0.0818 moles. Multiply by the molar mass of carbon monoxide, and we get 2.3 grams of carbon monoxide in the flask. Well, that wraps up the free response section, and it's the end of the AP Chemistry Practice Midterm exam. I hope that all of these answers and explanations were helpful. Thanks for watching, and good luck studying.